assume that the friction angle in undrained condition is equal to 0. 6.28 C plus Q is the equation for the upper bound solution. After that, we discussed about the Terzaghis bearing equation, and in Terzaghis bearing capacity equation, we derived that we can write that equation as where C is the cohesion of the soil, Q is the overburden pressure exerted onto the foundation, gamma is the unit weight of the soil, NC, NQ, and N gamma are the bearing capacity factors which are dependent upon the friction angle, and D is equal to the width of foundation. C and C, Q and Q, and half gamma, B and gamma, and we can also write this Q into gamma into D, and that D is the depth of foundation. Now, Terzaghis also proposed few shape factors SC and S gamma in order, we can call that as shape factors, and then in order to find the bearing capacity of different shapes of foundations. So SC and S gamma were the two shape factors which were proposed by Terzaghis. Now, in this lecture, we are going to focus on the Merhoff bearing capacity factor, bearing capacity theory, sorry. Basically, this is the extension of Terzaghis bearing capacity theory. Now, the failure mechanism assumed by Merhoff are presented here. For example, if we make half portion on the left side, this is for Terzaghis failure mechanism, and this one would be the Merhoff failure mechanism. Looking at this figure, we can clearly see that the alpha value in case of Terzaghis bearing capacity theory, that alpha was equal to the friction angle. However, in case of the Merhoff bearing capacity derivation, we can clearly see that the alpha angle is 45 plus V by 2. This is the angle which this elastic wing is making with
Excuse
the
me, sir.
horizontal surface. Yes, please.
सर आपकी वॉइस लेग हो रही है सर.
Okay. Let me change the location as well a little bit so that if you see any difference there. So when you see a little bit or if you hear a little bit difference in the voice, please kindly confirm that the voice is
Now it's clear, sir.
okay. Now it's clear. So I'm moving a little bit here. You know about the Wi-Fi signals are the eJorome signals which are working at the department. So sometimes it works, sometimes it won't. Let's see. Anyways, okay. So back to the lecture. Now, the important difference in the Terzaghis and Merhoff bearing capacity equations are here. For example, if you see, this is the slip surface which was proposed by Terzaghi. Now, this is the elastic wedge. This is the radial shear zone, or I would call that Prandtl zone. And then here we will be having a linear zone or the passive zone, a Rankine passive zone. And if you see here, the Terzaghis slip surface will end at the level of the foundation level. I would call that as foundation level. Here is the ground level, and the Terzaghis slip surface will end at the foundation level. However, if we look at the slip surface from the Merhoff bearing capacity theory, so we can clearly see that this portion is included in deriving the Merhoff bearing capacity equation. So the shear strength of this part is included in deriving the bearing capacity equation for the Merhoff. So this is the second difference which we can clearly see here. What would be the third contribution of the Merhoff to the for finding the bearing capacity of the soil? Now, one of the major contribution of Merhoff bearing capacity equation is that he proposed depth factors which will consider the depth or the increase in the bearing capacity with the depth of the foundation, shape factors, so in order to account for different types of different shapes of the foundations, for example, the square, strip footing, rectangular one, or the circular one, and the third, which are inclination factors. Okay? Inclination factors. Now, the inclination factors means that if vertical load is applied and horizontal load is applied onto the foundation, then there will be a resultant acting at a certain angle theta. Okay? This will be the resultant, and this would be the vertical load, and this one would be the horizontal load. So the resultant would be acting at a certain angle, and that we can call that as theta. So based upon the angle here, that theta, Merhoff proposed several bearing capacity, or we can call that as inclination factors. So IC, IQ, and I gamma. One more important point we can see here, that there was no shape factor in case of Terzaghis bearing capacity theory. So Merhoff also proposed a shape factor for the overburden part of the Terzaghis bearing capacity equation. So let me write again that this is due to the cohesion of the soil, and bearing capacity contribution due to the overburden, and also due to the weight of the soil beneath the foundation. So the shape factors are SC, SQ, and S gamma. The depth factor BC, BQ, and D gamma. We will come to the B prime, which is the effective width of the foundation. And gamma prime is the effective unit weight of the soil. Now, Merhoff also contributed that if the loads are eccentric in nature, which means that if a load is applied, for example, at the center here, that is known as concentric loading. But if that load is applied at a certain eccentricity E, so it will also cause movements. So at this point, or even at this point of the center, so that is known as eccentric loading, which will cause movement in this foundation. Please kindly note down this equation here, which is the Q ultimate equal to CNC DC SC IC gamma prime DQ NQ DQ SQ and IQ, half gamma prime B prime N gamma D gamma S gamma and I gamma, which is very important, which will be used in solving examples and problems. Now bearing capacity factors. NC, NQ, and N gamma, as I mentioned earlier on, are the bearing capacity factors, which are dependent upon the friction angle. Okay, and you can find out the different bearing capacity factors using these equations. Please kindly note down these equations as well. Now, if you want to find out the shape factors, so Merhoff proposed the shape factors, which are also dependent upon the friction angle and the effective width of the foundation. And I will explain what is the effective width in detail after a few minutes. Effective width of the foundation and effective length of the foundation. Effective length. Okay. Now Kp is the lateral earth pressure coefficient at in passive condition, and you can find out the Kp using tangent square 45 plus phi by 2, and that phi we can obtain from the direct shear test, or we can find out using the triaxial test. Now if friction angle is greater than 10 degree, or for any case, then we can greater than 10 degree, then you will use this equation to find out the SQ and S gamma shape factors. If we are given with phi equal to 0 degrees, then you will use SQ is equal to S gamma equal to 1. So both these shape factors will become equal to 1. The depth factors, Merhoff also proposed these depth factors, and these are the depth factors for any phi. You can find out dc 1 plus 0.2 under root kp d by b prime. D is the depth of foundation, and dq and d gamma will be equal to this equation, where kp is the lateral pressure coefficient in passive condition, and it is given here. dq and d gamma will be equal to 1 if the friction angle is equal to 0. Now you might be thinking that how we got these equations and how we got we are picking these, or we are selecting these equations to be used for bearing capacity of the soil. There is a history behind that, and that history will be explained in a research paper which I have already shared on the Google Classroom, where you will see that how the failure mechanism and how the different researchers or various researchers came to these equations. And then the comparison is also given with the finite element software, which is known as Plexus, which is very powerful tool to find out the shear failure or bearing capacity and settlement analysis or the stability analysis. Okay, so I will show you a paper. Please confirm that the voice is clear and the screen is visible.
Yes, sir. Voice is clear and screen is visible.
Okay, thank you very much. Now I will need your help here to read me out the highlighted text. So I need like 3 volunteers in the class so that we can carry on with the discussion here as well. So I would request the 3 students, the 3 volunteers, that they can read me out the highlighted text A and for the discussion as well. Okay, so who is the first volunteer?
Yes, sir.
Name please, because I'm not looking at the
Ashhad Zawar.
Okay, thank you, Ashad. First of all, let me tell you, this is a research paper, and a research paper you write when you do or you want to pursue the higher studies. So here is the title of the journal. Let me see if I can write somewhere. Okay, so this is the title of the journal, Innovative Infrastructure Solutions. It's a technical note, which means that the work here is brief work and not the very detailed work or very innovative work, but still the comparison is made with the previous research. Here is the title of the paper or the technical note. It says that numerical check of the Merhoff bearing capacity equation for shallow foundations. And that's what we are interested in. So Ashad will help me out with the abstract, reading the abstract of the paper, and will, where I tell you that please stop, then I will explain that portion. So you can please continue.
Most geotechnical design in books use the equations of Merhoff or Terzaghis to calculate shallow foundations. These equations are based on the failure mechanism published by Prandtl for shallow strip foundations. The
Okay,
common idea.
please look. The thing is that we say that Terzaghis proposed that mechanism, but actually this is the Prandtl shallow, the failure mechanism which was proposed by the Prandtl, and this is the portion which I told you that this is the portion which Terzaghis named the radial zone, the radial shear zone. That is the Prandtl zone in case of Terzaghis bearing capacity equation. Okay, please continue.
The common idea is that failure of a footing occur in all cases according to Prandtl wedge failure mechanism. To check the failure mechanism and the equations of currently used bearing capacity factors and the correction factors, a large number of finite element calculations of strip and circular footings have been made.
Okay,
The
please wait. Please wait now. Finite element calculation of strip and circular footings have been made. So there is a software named Plexus, and that is available in 2D as well and 3D as well, where you can easily perform the bearing. You can perform and you can find out the bearing capacities of the soil or the load settlement curves there, which will give you an idea that how this foundation will fail in shear and how this foundation will settle. Please continue.
The finite element calculations show that in case of soil with high friction angles, soil without cohesion or a surcharge footings with inclined loading or circular footing, not the Prandtl wedge failure mechanism, but other failure mechanism occur.
Okay, please wait. Now, look, the thing is that this is an idealized failure mechanism. It was proposed to derive an equation and to give us an idea that how we can estimate. So it was kind of a rough estimation to find out the ultimate bearing capacity of the soil. Now, in order to check that, there are finite FEM softwares are available, and we can check the bearing capacities, or we can check the different types of bearing capacity factors, or the correction factors, inclination factors, slope factors as well. So if we do that, the researcher noticed that the Prandtl wedge failure mechanism was not occurring. In addition, yeah, please continue.
In addition, the currently used equations for bearing capacity factors and correction factors are too high. Therefore, new equations have been presented in this article for some correction factors, for example, the inclination factors and the cohesion, slope factor, and analytical solution is found.
Okay, thank you very much, Ashad. Now, this is the abstract, which gives you an idea that what we are going to read in this research paper. So a Prandtl wedge is given, and I would request the volunteer number 2 to read me out the Prandtl wedge highlighted text. So who would be the volunteer number 2? Volunteer number 2, please. Okay, may I choose then? Atif Ali, can you hear me? Okay, Atif Ali is gone. Adil Khan, can you hear me?
Yeah, yes, sir.
Okay, Adil, please read me out the text which is given here beneath the Prandtl wedge,
Yes, sir.
the highlighted text, okay?
Bismillahirrahmanirrahim. Yes, sir. The Prandtl wedge, the origin of design shallow foundation leads of the mechanism. Mechanical engineer Ludwig Prandtl in 1920 called about the hardness of a plastic body.
Okay, so
The
please wait.
function Prandtl
Now,
was
please
meant to
wait.
find out at which load fully.
Okay, please wait. Now we see here the bearing capacity history started with the work of Prandtl. In fact, it goes back to the Heinrich Hertz because he got motivated from studying his work, and then it was studied by the Prandtl, and then it comes to the Terzaghis, or we call that as Reisner, and then it will come to Terzaghis work. Anyways, this is the way which is followed, and the shear strength of the soil using the friction angle and cohesion were compared. Now, the drawing of the failure mechanism proposed by the Prandtl can be seen in figure 1 here. So this was the failure mechanism, the Prandtl wedge failure mechanism, where you can see the elastic zone, the radial shear zone, and the passive or the Rankine passive zone. Three zones are presented: zone 1, zone 2, and zone 3. Okay, now please continue, Adil, from here till here.
The solution of Prandtl was extended by Reisner with the surrounding surcharge Q. Kelvin Besman and Terzaghis extended the Prandtl-Reisner formula for soil weight gamma. It was Terzaghis who first wrote the bearing capacity with the three separate bearing capacity factors for the cohesion, surcharge, and
Please,
soil weight.
please,
Merhoff was
please
the
wait.
first to propose.
Okay, it was Terzaghis who first wrote the bearing capacity with three separate bearing capacity factors for the cohesion, surcharge, and soil unit weight. So that was the contribution of Terzaghis. Now we will see the contributions from Merhoff. Okay, please continue from Merhoff.
Merhoff was the first to propose equation for inclined loads based on his own laboratory experiments. He was also the first in 1963 to write the formula for the vertical bearing capacity phi v with the bearing capacity factor n, inclination factor I, and shape factor s for the three independent bearing components cohesion c, surcharge q, and soil weight gamma. In a way, it was adopted by French Hanson and can be found in most geotechnical design codes and books.
Okay, thank you very much, Adil. Now, these are the significant contributions proposed by Merhoff. Okay, and due to the inclination factors, shape factors, and also considering the movements there, then in North America, most people use, or even here in Pakistan as well, use the Merhoff bearing capacity theory. However, in Europe, people use the Hanson, or even they call that, for that equation, the lengthier equation which we discussed a few minutes earlier on. That equation is also known as Hanson equation, because Hanson proposed the slope angle. So, and for the sloping ground, if you want to build a foundation on top of the a sloping ground that is known as beta, so for that case, how it's going to affect the bearing capacity, because so far we are only focusing on the level ground, but there are other people, for example, the Hanson, he proposed for the sloping ground that how the bearing capacity will be affected with the sloping surface. Then Vesic came and he proposed the bearing capacity, for example, for the inclined foundation as well. So these are the things which were adopted in by various researchers in order to find out the bearing capacity of the soils, and how bearing capacities were derived, what were the parameters on which these bearing capacities are dependent upon, and all these bearing capacity factors and also the inclination and shape factors can be checked with the FEM calculations. And then he compared it with the Plexus software. And different failure mechanism can be investigated using the numerical check or the numerical analysis if we perform. So we give certain parameters to the soil, and then we see that how the stresses are transferred into the zone 1, zone 2, and zone 3. So this is the Prandtl wedge, where the friction angle or loose sand is used. I would call that, because the friction angle is very low. And if the dense sand is used, so you can clearly see that we are experiencing a different kind of failure. Here it's kind of a 3 zones failure mechanism, but we are having a kind of, the elastic wedge type of failure in case of very dense sands. So this is the numerical comparison. Now changing the inclination factors, then what are the equations to use and to find out the inclination factors. Merhoff performed model tests in sand and in cohesive or cohesionless soils in both cases. For example, he changed the inclination of the load. Right here. So if we want to draw foundation something like this, straight one, yeah. Then he changed the inclination. For example, it's 0 here now. Then it will change at a certain angle, and the resultant will change at a certain angle, and then he will find out what is the Q ultimate using Merhoff bearing capacity equation. 10, I would call it 10 degree, for example, 45 degrees. And then so that's how the bearing capacity was found by the experimental tests. Okay, and you can measure the loads and deformation using the dial gauges which are available in the labs, in geotechnical labs. It's kind of a shear box. You can clearly see here is a kind of a box, I would call it, not the shear box, but it's kind of a box where you can push this foundation into the soil. Now, then with different inclinations, the more circles, in comparison of the shape factors, here you can clearly see the inclination angles, that how the researcher changed the inclination of the load which is applied on top of the foundation, and the comparison is made here as well with different kind of soils. For example, if the cohesion is 10 kilopascal, or if the friction angle is 0, or if the friction angle is 35, how the failure mechanism beneath the foundation would change. So here we are seeing higher stresses here, and we can clearly see lower stresses as we go beneath the foundation. So it's the failure mechanism of circular areas or circular foundations with having low friction angle and high friction angle. And then slope factors were also studied. So Adil, please kindly help me with the reading out the slope factors, highlighted text.
Yes, Merhoff was in the 1957 the first to publish about the bearing capacity of foundation and slope. He wrote, foundations are sometimes built on sloping sides or near the top edge of a slope. When a foundation located on the face of a slope is loaded to failure, the zones of plastic flow in the soil on the side of the slope are smaller than those of a similar foundation on level ground, and the ultimate bearing capacity is correspondingly reduced. Merhoff proposed a failure mechanism of footing in a slope with angle beta on the figure on the left side, and introduced figure with the reduced bearing capacity factors.
Thank you. So as the sloping surface is there, or if the load is applied at a certain slope and the foundations are constructed at the slope, the bearing capacity will reduce. And the effect was also studied in the finite element software, Plexus. Different shape factors. Here we can see that how the elastic wedge shape will change when a foundation is constructed in a sloping surface having angle beta. Okay, so in degrees you can call that failure mechanism of a footing in a slope, and you can clearly see that how the failure wedge shape is being changed. Now first we change the inclination angle, then now we are changing the slope angle. Okay, and we are observing the Prandtl wedge. In this case you can clearly see those three zones. Now these three zones can also be seen here as well. Now you see the change in which is occurring in the failure mechanism with different beta values or angles. Then a conclusion was proposed, and I would request the third volunteer to read or to help me out with the conclusions. So who would like to be a third volunteer? for today's class. Okay, let me pick Ejaz Azim Khan. Can you hear me? Shah Fahad, can you hear me? Ejaz Ali, can you hear me?
Yes, sir.
Okay, Ejaz, please help me out with the conclusions highlighted text.
Okay, sir. A large number of finite element calculation of strip and circular footings on a homogeneous soil have been made to check the failure mechanism and to check the currently used equations for the bearing capacity of factors and inclination factors and shape factors.
Okay, so different factors were investigated, and they were changed. Now, slope factors, now the FEM calculations. So you can start with the finite element calculations.
And slope factor. The finite element calculation show the currently used bearing capacity factors are too high. The most important reason for this is that for natural soils, the dilatancy angle is much lower than the friction angle. The finite element calculation also show that not in all cases a Prandtl wedge failure mechanism occur. In fact, in many cases, other failure mechanism occur. There is one of the reason why most of the currently used inclination, shape, and slope factors are not correct. In many cases, the currently used correction factors are too high, so unsafe. Therefore, based on the finite element calculation, new equation have been presented in this article for some correction factors. For example, the inclination factors and cohesion slope factors. Analytical solution is found.
Okay, thank you very much, Adil. Now we can clearly see that how the comparison was made using different shape factors, bearing capacity factors, inclination factors, the slope factors as well. Now the ground factors as well. Now we will see a video here, if I have somewhere. This is the Plexus software, that how we can find out the bearing capacity of the shallow foundation. So I will show you quickly the dimensions, how they start with the project. The square footing is there, 2 by 2 meter. The gravity or the unit weights information, the boundary conditions. Then you draw the foundation, the soil information is also given. So it shows you how you can use the Plexus software, which is very important software. Please download if you find out the software online, which can be very, very handy for finding the bearing capacity of shallow and deep foundations. So you will draw the foundation, then you will assign the properties of the soil. For example, let me show you, if we can go here. So soil properties are getting assigned: drained condition, undrained condition, more Coulomb failure criteria, unit weight, unsaturated, saturated unit weights, how they assign it, Poisson's ratio, elastic modulus, cohesion and friction angle values. You can choose the color of that material as well. For example, if it's clay, if it's sand, and then for concrete, linear elastic, non-porous, the properties are here, and you can give those properties as well. And then there are different phases. Initial phase, first we excavate, like here, the initial phase excavation, then the footing is casted there, and then the loading is done. You can also choose the water table effect as well, and then you run the analysis, and in analysis you will see the load settlement curves there and the stresses information. So this is the load settlement curve, it's load and settlement curve. Now we will see. Okay, let me show you this one here as well, so that you can see that how the deformation is occurring beneath the foundation. Let me see if we can get the contours somewhere. It was very brief there. Yes, here. Now you can see that how the stresses are distributed beneath the foundation. So it's the high stress area and the deformation is high. Okay, different parameters. When we or you use the tutorials, then you can extract that data, export it to the Excel. You can draw the figures as well. This will be, this will give you a load settlement curve. So now you can see that this is the settlement, and here is the load which was applied. 4,000 kilonewton was applied. So that's how you can use this software as a geotechnical engineer, which is used mainly in North America as well, here in Pakistan and all around the world. Now, as a, this is specifically how we can use it for shallow foundations. Now, how effective it is for different types of geotechnical structures. Now you can please watch this short video. Okay, thank you very much for watching. Now we will discuss and come back to the lecture. But before coming back to the lecture, if this is a very fundamental research which is conducted on the bearing capacity of the foundations or the shallow foundations and deep foundations. So if someone is interested in performing, or if he is interested in performing the numerical studies and analytical studies for shallow and deep foundations, I would be more than happy to work with that group who is interested in doing the analytical and numerical studies. And also maybe we can continue with the model test as well, because you can clearly see that there are researchers who worked on the uh, different equations comparisons with the standard or the fundamental theories which are proposed for the shallow foundations, and we will also compare that for the deep foundations in the later stage of that project. So if someone is interested, if some group is interested in that, please do let me know so that we can carry on with the FIP as soon as possible. Okay, now we discussed about the inclination factors. So if a vertical load is applied and the horizontal load is applied, then the resultant which will be acting at a certain angle theta. Now, how the horizontal load and moments are generated, that is due to the wind loading which is acted on the superstructure. Now, bending moments are common for structure such as retaining walls. Retaining walls. And how we can find out the inclination factors, for example, IC, IQ, and I gamma. Please kindly note down these equations because we will be using these equations in solving numericals and problems. Now, we discussed in detail the differences between the Terzaghis and Merhoff bearing capacity theories. Merhoff shape factors do not differ greatly than those of the Terzaghis, except for the addition of the SQ factors. SQ was added by the Merhoff. Exit wedge, that portion, the shear strength of that soil was also not present. Now the D is approximately equal to, or the depth of the foundation is equal to the width of the foundation, and if it's equal to the width of the foundation, then it would be approximately equal to the Terzaghis bearing capacity theory answer as well. If the D by B is greater, significantly greater, then we will see the difference between the Merhoff and the Terzaghis equation. Terzaghi theory can be used for very cohesive soil and for shallow foundations. We can get a quick estimate of the ultimate bearing capacity of the soil, but we are unable to use or to get the bearing capacity of the horizontal forces or for tilted bases and for the sloping ground. Now we can use Merhoff equation for any situation. For example, we can add the depth factors, we can add the shape factors, we can add the inclination factors, or even we can add the slope factors are the ground factors to account for the sloping load inclination and also for the sloping surface and also for the ground if the foundation is inclined as well. We discussed about three types of failure modes. For example, there was a general failure mode, there was a local shear failure mode, and there was a punching shear failure mode. So the Terzaghis and Merhoff equation assumed this type of failure mode, which is the general shear failure mode. Now, in order to use these equations for local shear failure mode, you need to slightly modify the shear strength parameters. For example, we need to divide the cohesion value which we obtained from direct shear test or from the triaxial test. So these values we need to reduce a little bit by two-third, and then we will divide that by two-third or multiply that with the two-third of the tangent phi as well. So phi double prime and c double prime are the revised, I would call it, or modified shear strength parameters which you are going to use if you want to find out the bearing capacity using Terzaghis bearing capacity equation for local shear failure mode. Now, we already know that the CNC term is predominantly due to the cohesive soils, and the overburden term, which is the Q and Q, is predominant in cohesion-less soils. For example, this is for clays, this is for sands. Now, the self-weight beneath or the breadth term here provides some increase in bearing capacity both for the cohesive and cohesion-less soil. But for the case of B less than 3 to 4, it can be neglected as well. Now, we discussed a little bit about the eccentric loading, and eccentric loading basically, for example, if we are given with a foundation, please confirm that you can hear me and the screen is visible.
Yes, sir.
Okay, thank you very much.
Hello, sir.
انا सर तकाल या मैसेज का से ना पता होता नहीं कि और डिस्कनेक्ट शो मुंह तो हुई सर यस सर और बस पागा टाइम डिस्कनेक्ट शो
Hello.
And plus 10x square divided by 9.
Hello. सर जी सब पता
जी
नहीं
जनाब
सर जी सब पता नहीं गाना से सर
इस पता न लगी नस्ता को मुंगो ino का नस्ता तो वो क्या ना
सही है जी yo बोलता पोस्ट को मतलब उसका ये फाउंडेशन वाला ग्रुप था व्हाट्सएप ग्रुप
ना फाउंडेशन वाले स्पेसिफिक नहीं था वो जमुन खपल यो ग्रुप स्टडी द क्लास वाला
अरे ये हमारा संग ऐड के
Anas Khan yedi da CR'de. Dede bu vedi etkida adminde. Anas Khan ne message होता कि chat box के.
أنس خان اشتغل موجود ده. أنس خان لو أنس خان
Hello, can you hear me?
Yes, sir.
Yes sir.
Where I left the class?
Here in law. हाँ sir.
How
Sir, when you
long?
told us about that, my voice is clear and the screen is visible.
No, when you need to help me out here.
Yes, sir. Sir, share this in screen so we will tell you.
Okay, let me. You need to call me then.
सर आप हमारे साथ अपना नंबर शेयर करें ना.
नहीं अरशद, आई थिंक सो अरशद के पास तो है मेरे ख्याल में.
सर मेरे पास नहीं है सर, अनस के पास है, CR अनस है.
अच्छा, अनस के पास तो अनस को अनस, वेयर आर यू? अनस.
यस सर. सर मैंने तो आपको मैसेज किया था सर.
यार मैसेज खुदा का खौफ करो यार, मैसेज कैसे करो? मैसेज मैं देखते ही नहीं हूँ क्लास के दौरान. कॉल कर लेते बस.
ठीक है सर, सॉरी सर.
12:15 पे 12:15 पे 6 मिनट्स हो गए. 6 मिनट्स में तो मैंने काफी चीजें एक्सप्लेन कर दी हैं. मेरे मौला रहम फरमा ले. रमजान भी है और आप लोग कॉल भी नहीं कर रहे हैं तो मुश्किल हो जाएगा. अब कहाँ पे थे अभी देखने, इतनी एक्सप्लेनेशन.
सर इससे नीचे वाला सर, इससे नीचे.
अच्छा ये स्लाइड है.
सर ये हुआ था सर.
शुक्र है ये हुआ
इसके
था.
बाद
चलें.
वाला.
ये हुआ था.
हाँ ये वाला भी सर.
पुटिंग जो एसेंट्रिक
ये
लोडिंग
हुआ.
ये नहीं हुआ था.
हाँ सर ये डायग्राम, हाँ यहाँ पे थे सर के, बस आप
देखिए
disconnect
यहाँ
लेते.
पे
ये आप explain.
बेसिकली बात ये है कि हमारे पास इफेक्टिव एरिया होता है. अगर लोड हमारे पास ऑफ द सेंटर होता है तो फिर जो एसेंट्रिसिटी है वो EB और EL. EB जो कि एसेंट्रिसिटी इन द डायरेक्शन ऑफ विड्थ ऑफ द फाउंडेशन और एसेंट्रिसिटी इन द डायरेक्शन ऑफ द लेंथ ऑफ द फाउंडेशन. फिर हमारे पास ये जो ग्रेश एरिया है, ये एरिया हमारे पास इग्नोर किया जाता है कि ये कुछ लोड अप्लाई नहीं करते. ठीक है. फिर हमारे पास होता ये है कि एक इफेक्टिव एरिया आ जाता है. ये इफेक्टिव एरिया है जो कि लोड को अप्लाई करता है ऑन टू द सॉइल. और फिर इसी इफेक्टिव एरिया के नीचे जो सॉइल है वो हमारे पास इसको रेजिस्ट करती है या बियर करती है. अगर हमने EB को फाइंड करना हो तो मूवमेंट्स इन द B डायरेक्शन डिवाइड बाय द वर्टिकल लोड PV और वर्टिकल लोड. ठीक है. फिर अगर हमने EL फाइंड करना हो तो वो मूवमेंट्स इन द डायरेक्शन ऑफ द लेंथ ऑफ द फुटिंग डिवाइडेड बाय द वर्टिकल लोड अगर हम करते हैं तो हमें हमारे पास EL मिल जाएगा. तो इफेक्टिव B जो है ना, B प्राइम जो इफेक्टिव विड्थ ऑफ द फाउंडेशन है, जो कि मेयरहॉफ की बियरिंग कैपेसिटी इक्वेशन में इस्तेमाल हुई है, उसको हम कैसे फाइंड कर सकते हैं? उसको हम ऐसे फाइंड कर सकते हैं कि हमारे पास B तो ऑलरेडी मौजूद है, अगर हम उससे 2EB माइनस करते हैं तो हमारे पास ये लेंथ आ जाएगी. सिंपल. एक्सक्यूज मी. अच्छा, अभी अगर हम इफेक्टिव लेंथ फाइंड करना चाहें तो L प्राइम जो है ना वो हमारे पास L माइनस 2EL हो जाएगा. यहाँ पे 2 ऐड करनी थी. तो ये हमारे पास इफेक्टिव लेंथ L प्राइम आ जाएगा. ओके, रिकॉर्डिंग हो रही है वैसे. चले रिकॉर्डिंग में दोबारा आ जाएगा. कोई मसला नहीं है। अच्छा अभी नाउ आई नीड, अच्छा यहाँ पे हमने लार्जेस्ट और लोवेस्ट प्रेशर के बारे में फिर एक अल्टरनेटिव अप्रोच था। अल्टरनेटिव अप्रोच ये था कि अगर एक लोड एक्ट कर रहा है इसेंट्रिसिटी पे ई पे, तो उसमें इस साइड पे लेफ्ट साइड पे हमारे पास लार्जेस्ट बियरिंग प्रेशर जनरेट होगा और यहाँ पे हमारे पास लोवेस्ट बियरिंग प्रेशर जनरेट होगा। फिर उसमें Q क्या चीज है, Q हमारे पास वर्टिकल लोड है, Q प्राइम जो है ना हमारे पास लार्जेस्ट बियरिंग प्रेशर है, Q डबल प्राइम हमारे पास लोवेस्ट बियरिंग प्रेशर है, और E इसेंट्रिसिटी है, और B हमारे पास वेट ऑफ द फुटिंग है। अभी मैंने रिक्वेस्ट ये किया था कि आप लोग है ना ये बताएं कि कंसोलिडेटेड ड्रेन्ड और अनड्रेन्ड बिहेवियर नॉर्मली कंसोलिडेटेड क्ले के लिए और कंसोलिडेटेड क्ले के लिए कैसे होता है, वो जो जियोटेक 2 में हमने पढ़ा था। तो दो स्टूडेंट्स या दो वॉलंटियर्स अगर एक्सप्लेन थोड़ा सा कर लें। कंसोलिडेटेड ड्रेन्ड बिहेवियर और कंसोलिडेटेड अनड्रेन्ड बिहेवियर में क्या फर्क है?
सर क्ले के लिए हम कंसोलिडेटेड अनड्रेन्ड बिहेवियर कंसिडर करते हैं। जो हम टेस्ट से रिजल्ट लेते हैं तो वो भी अनड्रेन्ड, क्योंकि हमारे पास क्ले बहुत टाइम लेता है ताकि उससे ड्रेनेज हो हमारे पास, क्योंकि इसके पार्टिकल्स बहुत स्मॉल साइज के होते हैं। तो उसके लिए हम जो टेस्ट रिजल्ट लेते हैं तो वो हम अनड्रेन्ड कंडीशन वाले लेते हैं सर।
एक्सीलेंट, जबरदस्त। उसमें पोर वाटर प्रेशर की क्या सिचुएशन होती है?
क्ले में सर
हाँ, पोर वाटर प्रेशर इंक्रीज होगा डिक्रीज होगा, कैसे होगा अगर हमारे पास अनड्रेन टेस्ट और ड्रेन टेस्ट हो?
सर जब हमारे पास अनड्रेन टेस्ट हो तो पोर वाटर प्रेशर जनरेट होगा हमारे पास।
गुड, जबरदस्त, क्योंकि उसकी परमेबिलिटी लो होती है।
लो
जो
होती
सैंड
है
के लिए
सर।
क्या सिचुएशन होगी?
सर ड्रेन होती है, क्योंकि उसके पार्टिकल साइज बड़े होते हैं और वो परमिएबल होता है, तो उससे ड्रेनेज इजीली और जल्दी हो जाती है। तो उसके लिए हम ड्रेन सिचुएशन लेते हैं सर।
एक्सीलेंट, चलो चलिए, थैंक यू वेरी मच अरशद। नाउ as Ashad explained, but I will add to a little bit to these figures which you have already seen during Geotech 2 for the normally consolidated clay situation or for loose sands. If you want to draw the sigma D behavior, which is the deviator stress during the shearing stage of the specimen, and that sigma D we can also write down as sigma 1 minus sigma 3, and this is the axial strain. So if you want to draw the stress strain behavior, this will look like this for normally consolidated clay or for the loose sand. Now if you want to draw this pore water pressure behavior, so we can clearly see that for loose sand the pore water pressure is positive, because the soil particles or the sand particles try to compress. Now if you want to compress in the undrained condition, the positive pore water pressure will be generated. Now if you want to draw the stress strain behavior for the over consolidated clays or for dense sands, the stress strain behavior will look like this one, almost the same. It should go a little bit higher because it's dense sand if you are comparing these two, but anyhow, no problem. And the pore water pressure will initially increase and then it will decrease for the OCR, for example 1. Now then for the increasing OCR 3, and for the increasing OCR, now you can clearly see that the positive, the initially for this portion the pore water pressure is positive, and for this portion the pore water pressure is negative, or we can call that as in negative here as well, or the positive here as well. So you can see this much pore water pressure magnitude has been dissipated, and this is the strain level, because this is the axial strain. Till this point of the axial strain, the pore water pressure was positive, and then it was negative, and then it was leveled off. Similarly, if we want to note down the behavior of consolidated drained test, so sigma d and delta, the volume will change. So we can draw the stress strain behavior, something like this, and the volumetric behavior, because it is negative, which means it's compressive for the normally consolidated clays and for loose sands. For the case of over consolidated clays or dense sands, we can see the stress strain behavior at very small strains compared to the other one. You can clearly see here, you can see the strains are quite high or greater to reach to the peak strength. Here the strains are very low to reach to the peak strength. For example, if we start with the lower OCR sample, OCR having 1 and OCR having 3, OCR having 4, so you can clearly see that the dilatancy of these type of soils, the dense sand, will increase with increasing the density or the OCR of the clays. So that was just a recap to the what we discussed in Biotech 2. Now for sands, we mostly perform the drained analysis or undrained analysis. For sands,
analysis.
we mostly perform drained analysis. It is also known as effective stress analysis, and it is also known as the long-term stability analysis. Okay. Now for the clays, we will, okay, now for sands, sometimes we discussed that undrained analysis are also performed when we are dealing with the blast loading or earthquake loading, but mainly we are concerned more about the drained strength of the sands. Now for clays, we need to perform the total stress analysis, which is the short-term condition, or which is also known as the undrained condition as well. And for the long term, this one is the drained condition. Now for total stress analysis, we need to find out the undrained shear strength, of the soil or of the clays, and for that purpose we need to perform the vane shear test, the unconfined compression test, unconsolidated undrained test, or we can also perform the consolidated undrained test as Ashad mentioned in our earlier discussion. So these shear strength parameters can be known as the total strength parameters. Now, for example, if you want to please confirm that the screen is visible and the voice is clear.
Clear, sir.
Okay, thank you. So there are two examples which we can give for understanding the consolidated undrained behavior, and then if we are having grains, wheat grains, or we are having an oiled tank. So if we empty this oil and if we empty these grains from the grain elevator or the oil tank there, and here is the soil, saturated soil, and we then immediately again fill this grain elevator or the oil tank. So first the soil was in consolidated condition, but now we are again adding, we are emptying, and then we are again adding this oil into this oil tank or the grain elevator. So this would be the simulation of consolidated undrained test. Now for the case of the clays, the effective stress analysis of clays should be performed for normally consolidated clays. Okay. Now, for example, for the soft clays, this one we can remove. For the soft clays, we will do the normally consolidated clays. So we are more interested in the short-term condition. And for short-term condition, what type of analysis we perform? We perform the undrained, or we perform the short-term analysis and we can also derive an equation which is pretty much simple, having the friction angle equal to 0. The bearing capacity factors can be found out, and approximately we will come up with the Q ultimate net equal to the Q ultimate of that soil. Now for heavily over consolidated clays, we usually perform the effective stress analysis. The reason behind that is that in case of heavily over consolidated clays, negative pore water pressures are present, and these negative pore water pressures increase the shear strength of the soils. So we need to wait that these negative pore water pressures equalize and we get the final pore water pressure condition, so that to find out the strength of the soils, and that can be obtained in the drained shear strength behavior or the effective strength behavior stress analysis, or in the long-term condition. For the case of heavily over consolidated clays, in heavily consolidated, we need to perform both the total plus the effective stress analysis. These problems will be solved in the coming class, and all these equations will be used, which I mentioned that are important for exams and the quiz assignments purposes. Now there are two design philosophies. For example, one is the allowable stress design philosophy, and the another one is the ultimate limit state design philosophy, or the limit state design philosophy. Chapter number 2, which we discussed so far regarding the Terzaghis bearing capacity equation and also the Merhoff bearing capacity equations for the allowable bearing capacity and for the ultimate bearing capacity, and dividing it by the factor of safety. That approach is known as the allowable stress design philosophy because we get the allowable bearing capacity of the soil. And if the Q applied is less than or equal to the Q allowable, then we are on the safer side. There are different factors of safety, and we had a good discussion on why we choose the factor of safety depending upon the soil type, because we get different types of soils in the field. Site investigation will vary. We can perform standard penetration test, we can perform the cone penetration test. So different types of tests which we can perform at the site. The soil variability is there, and the importance of the structure and the consequences of the failure also determine the factor of safety. Now, in case of limit states design, what we usually do, we use the partial safety factors for the load and strength parameters. How we do that? We find out the factored loads by multiplying certain factors with the loads and forces, and we will find out the factored pressure, which will be divided by the area or the base area of the footing. So a load, we will apply some factors, for example 1.25 with the dead load, 1.5 with the live load, and then we will come up with the loading here. So it would be factored load, I would call that. The P is equal to 1.3 of the dead load plus 1.5 of the live load, and the area is here, for example, it's B, so we can take that B into B if it's a square footing, so square of that B. So if we divide the P divided by the area, we will get the applied pressure. Okay, the applied pressure on top of this soil. Now we will find out the design shear strength parameters by multiplying the shear strength parameters of the soil by the resistance factors. And what are these resistance factors, and why we apply those resistance factors with the design shear strength parameters? The design shear strength parameters are the cohesion and the friction angle. The design capacity of the foundation is calculated, and now to satisfy the ultimate limit state, the design capacity, so the design please confirm that you can hear me and the screen is visible.
Yes, sir.
Thank you. Okay, now the design capacity must be greater than or equal to the factored applied pressure. So here you can clearly see that resistance factors, for example, with the loads 1.2 or 3 dead load plus 1.5 live load, or even the resistance factors. So these are the factors which are given by various codes of the countries, and the resistance factors, for example, F C or F phi are applied, and for the FC it's 0.8 into the angle of friction which you get from the direct shear test, and for the cohesion it would is 1.5 till 1.7 you can get and multiply it with the cohesion. So you reduce the shear strength parameters and you increase the loads, and then you get the design capacity, and you compare and find out the design capacity should be greater than the factor applied pressures. Thank you very much for listening very patiently, and I was hoping to go for the problems as well, and we can go and solve a simple problem here today, and then we can start with the second problem from the next class. So please kindly solve this problem. We have like 5 minutes. It can be solved. In problem number 1, we need to use the Terzaghis bearing capacity equation, and here is the Terzaghis bearing capacity equation. And I told you to write down this equation because it's very important, otherwise you will be unable to find out the ultimate bearing capacity. So Q ultimate we need to find out. B is given 1.5, square footing is given, so SC and S gamma values can be taken from the table. Yes, if I remember correctly, it's like 1.3 and 0.8 something. Okay, it's given here as well. These are given, and the friction angle value, and then you can use the figure to find out the bearing capacity factors. And if you put those SC, S gamma, and C, and Q, and gamma, D is the depth of the foundation, it's the 1.2 meter. This is the unit weight, friction angle, cohesion. So you will come up with the ultimate bearing capacity of this footing or this soil would be 665 kilonewton per square meter. How to find out the bearing capacity factors? Let me show you. Okay, let's start with this one. So it was a square footing. For square footing, you can clearly see that S gamma is 1.3. Now SC is 1.3 and S gamma is 0.8. It was 20 degrees. Now for 20 degrees, this is the value for NC, around about 18. And how much is the value for here? It's around about 13, I guess. And okay, here. Now, for the case of N gamma, it's 2, 3, which 2, 3, 4, 5. I guess it's 5. Yeah. So approximately 17.7, 7.4, N gamma is 5. So that's how we can solve the and use the bearing capacity equations for Terzaghis and Merhoff one. And that's the end of the today's lecture. If you have any question, please kindly ask those questions.